Hello everyone, February the 10th. Great cheat day today. Oh, absolutely wonderful. Ooh. All right, let's do this. A hard question with 70% acceptance. Very fishy. Very fishy. All right, cherry pickup number 2. I've done this one before. I do not remember it. You're given a matrix, the field of cherries. Grid ij represents the number of cherries that you can collect from that cell. 2 robots. 1 is located top left, 2 is top right. Return the maximum number of cherries collection using both robots by following the rules. From a cell, robots can move to cells. So I was going to say 4 directions. No, it's actually straight down, which is I plus 1j. I plus 1j minus 1 is the left. I plus 1j plus 1 is the right. So it's a down, diagonal left, or diagonal right. When any robot passes through a cell, it picks up all the cherries, and the cell becomes an empty cell. When both robots stay in the same cell, only one takes the cherries. Both robots cannot move outside the grid at any moment. Both robots should reach the bottom row in grid. So we need to design a path for both of them such that when they reach the bottom row, they can collect the maximum number of cherries. So for this example, robot 1 take this route, robot 2 take this route. Wow, good routes. And for this example, it's this. All right, row 70. Okay, so it's very low. So O(n) squared. Probably even not O(n) squared, maybe O(n) quadrupled, right? 70 times 70 times 70 times 70, which is 4,000, 5,000 times 500. Maybe it's okay. All right, how do you think? Well, basically it's DP. Without a question, it's DP. So what we need to do is to find the state. What is the state? We need a state that can represent both robots. So easiest way is for the state just to be I1 J1 I2 J2, right? That will run O(n) quadrupled, right? O(n) quadrupled. So basically we know where this starts, and then we just go through all. But they can, right? They can meet at the same. That is fine, right? Wait, hold a second. Quadrupled. 70 quadrupled. Is that really possible? 70 quadrupled. What's the 70? Oh, 70 quadrupled probably is not possible, because 70 quadrupled is 24 million. 24 million is more than what was required. I think probably 70 O(n) tripled. Yeah, I can see O(n) tripled work, but O(n) quadrupled probably is not going to work. So need to be slightly smarter than that, okay? But anyway, from 1, I can compute like the maximum, like this one. If you don't consider 1, then the maximum will be this route, right? 3, 5, 5, 2. But then if you add the second one, that will be 1, 5, 5, 2. And the overlap doesn't count, so this actually calculus. So yeah, you have to consider them, the two, as a single entity, right? So how can I make the state? Interesting. Well, they are going to take the same number of steps to get down, right? And ideally they do not overlap, because if they overlap, that means we will take fewer. Maybe we can try to prove that they will definitely not be overlapping, because if they overlap, like if you say we can find a path that the two overlap and they get the best, and I can argue that they can do no worse than not overlapping. Yes, that's true. Therefore, we can consider them not overlapping, right? They do not overlap. Okay, and at each row, they must take two, right? They must take two. So at the end, we can say the two robots will take, some states, right? One is one and the other is the other. It doesn't really matter. Well, we have the start position, right? And then we go to the second round. And the second round, we say the max on one side is something. And the third round, we can say the max for one. Or, because at the end, what we want is, well, maybe what we can do, let me use this example, okay. Let's just do the, most basic DP that we know shall work. 2, 5, 1, 1, 5, 5, and then 2, 1, 1, right? So we say we want to know the max. So the max I can do reach this row. Okay, the max we can reach this row is 4, right? We pick these two. And then the max we can reach this row. Is that right? The max, actually that's not true. That's not true. We shouldn't do that. That is not true. I don't see, like, say each time you have to pick the maximum. That's not true. But each time I know what are the availables, right? What are the availables? Okay, if I do the max possible for one and the max possible for the other, how would that look like? So for robot 1, right? So we start from here. So the max possible here is 5 and 8, right? And the max possible to reach this cell, right? It's the max possible to reach this cell is, well, based on these three. So it's been 9. Max possible to reach this cell will be 13. Max possible to reach this cell is 13 as well. Max possible will be 15, right? This is 14, and this is 14. So that's robot 1. Okay, let's try robot 2. So we start with 1. That's 6. That's 2. So max possible here is 11. That's 11. That's 7. That's 12. That's 12. 13. So max possible for this is this, right? And then what? So the max possible here should be 15. 14, right? So we say it's a 15. Max possible is 12. But there is an overlap as we go through. Yeah, because the max is this path, right? Here, here, and then here. This is here, here, and here. That's the max path, right? And then within the max path, we have overlap. We have like this part. This is overlapping. Well, if it overlaps, I mean, it means one of them has to go through this, right? Either this or this. One of them has to go through this. Which means I can, just assign one of them to go through this. And then the other one, basically, I cannot go through. And for this one, if I cannot, then I have to go down. Because I cannot take this one. So this is out of the question. So I have to take this, right? And then if I take this, because I cannot take any one of this, so I can only take this. So that will be 1, 2, that will be 8, right? That will be 8, which is 23. But the answer is 24. Interesting. I think at a certain point, and they start at two opposite, so they start to go, and eventually, I mean, if the two paths do not, if they do not overlap, then that's just a two path, right? They just do not overlap. But if they do overlap, so one of them need to go some other path. How do I reason this? Can I say this just can be the max for each level? Because each level I say I find the maximum possible. Right? The maximum possible. If you say at a certain path, at a certain level, it's not the maximum, and you say that one will give you the maximum. That's actually, is that possible? At a certain level, let's say we have a giant value, then you have to take, no, because that one will be included. So it will be included when we do the computation, right? It will be included because it just expands, right? It expands. So you will find the maximum. So maybe we can try at each level, we find the combination that give us the maximum possible. Like, but there are two, right? There are two, so we have two locations that can make the maximum. So like on the first, hold on, maybe it's possible. I'm gonna have to take a look. Maybe there's some type of analysis that can allow us. Okay, so on the first, yeah, but it has, you know, just different combinations. So you start with different combinations, right? Actually, no, you start with this. You start with this and this. So to start with 4, right? Which is you take this and this, right? So you start with 0 and 0, 1, 2. 0, 2, that's what you start with. Now you come to the second. So from 0, you can do 0 and a 1, right? From 2, you can do 1 and 2. And we need to see, so there could be, and then you, let's say, do a set. So you have 0, 1, 2, right? These are the 3 possible positions. So you find a maximum, you say, okay, that's gonna, and then who is 0, who is 1, it doesn't matter. So in this one, we find 0, 1 is the best, right? 0, 1 is the best. And actually, no, it should be 1 from here and a 1 from here, right? So I can say, okay, if I had to pick 0 here, what do you pick? Can you pick 1? If you pick 1, now we have 7, so I have 0, 1. I have 0 and 2, so that's a 3, okay? And I pick 1. You cannot pick 1. You can pick 2. That's 6. So this one is 0, 1, right? 0, 1. So now we have 7. Next level, 0 we can do again 0 and 1. 1 we can do 0, 1, 2. So again, I pick 0, right? So 0 will be, I can do 0, 1 or 0, 2, the same. 0, 1, 0, 2 is the same, but that's 6. Or I can do 1, 1, 0. 1, 0 is the same as 0, 1, right? 1, 0 is the same as 0, 1. And then we have to figure that out. All right, we have to figure that out. So we have to sort them. Okay, sort them and find out if it has already been considered before. So 1, we might as well just only get larger, right? Only get like 0 cannot consider, 1 cannot, so we're gonna do 1, 2. 1, 2 is a 5, 5 is a 10, so we do 1, 2, right? So we have 1, 2, right? And then the last 1, 2, 1 we can do 0, 1, 2. 2 can do 1, 2. Okay, so 0. 0, 1 is 3. So 3, that's good. Right, 3, that's good. And 0, 2. 0, 2 is also 3. That's a 3. 1, 1, 2 as a 2. Now good. 2, there's no way. So this is a 3. So at the end, the answer is 24. And in this case, it's the same. Maybe. Okay, give this a shot. And today is going to be Python because... oh, Lord. PUY. Unbelievable. Oh no. Shoot. Should be about 11. Pi. Oh no. That's not Python, man. Damn. Oh, here we go. Unbelievable. I need to write a script to do this. Otherwise, it's gonna piss me off. Exactly. It's just make these silly mistakes. Oh, this is not Python, dude. What the hell? Man. This is Python. Okay. Alright, so what do we say? What we're gonna do is a type of, I'll call it BFS, right? It's a type of BFS. And at each we have a queue, and we need to do that as a set, right? And then we start with 0 and, okay, let me do this. mn equal to len grid and grid 0, okay? So that's mn. And my argument is we will find, oh, immediately you're wrong. Because in here, if you find the maximum, it will be 2, 3. But you're supposed to get 0, 3. Oh. Now what? Now what? But you can get all the pairs, right? It's not that much. Maybe you can get all the pairs, because for each one, you can get whatever the pair, because there's only 3, right? There's only 3, and it starts to grow, right? It starts to grow, you'll get more. But you know what? Maybe that's not that bad. Maybe that's not that bad. Because at each level, right, you get everybody. This one gets, so that's O(n) squared for each row, and at times the how many you have to go. That's O(n) tripled. Now O(m) times n squared. Yeah, I think that's maybe. So that's the start. We have a queue, and what we're going with at each one, we basically accumulate, right? We accumulate the sum so far, right? We accumulate the sum so far. If we pick this and this, what will be the sum, right? And at the end, the last one, we simply compute the maximum, right? We compute the maximum. So basically here, we're gonna do these two, and we say grid 0, 0, right? And well, plus grid 0 and n minus 1. Okay, that's our starting position, right? That's our start. Oh, No, we don't have to do a set. Do we have to do a set? Do we have to do a set? No, because when we start to iterate through all the possible combinations, we always go small and big, right? If we go small and big, then it will not be possible to even have a duplicate, right? To even have a duplicate. Therefore, this does not have to be a set. We can as simply use a array for this, which means we can actually do this in Java as well. But we're already committed to Python. We're just gonna keep doing Python. That's the queue, right? And then this is gonna be for I in range. Actually, we don't even need I. We do need I. For I in range from 1 all the way to n minus 1. I don't want to go all the way down because I need to, you know what? That's actually fine, right? We'll go to the last one, and because that will create a new queue, right? I'll create a new queue. So the last one, so we go 1, 2, 3. Because this one will create 1. Yeah, to m. Okay. Each time I have a temp, and then we just say for. Let's not say I. That's fine. For J1, J2, and S in Q. All right. J1, J2, and the current, the sum, right? Then for J1 I have a bunch. For J2 I have a bunch. Oh, I see. I might have the same thing, but they will have a better value. So I actually need to have that as, so it's not gonna be a queue, not gonna be in the list, it's gonna be a dictionary. It will be a dictionary, okay. It will be a dictionary. It will be a dictionary with a tuple of your J position as the key, and oh, that's not what we want. Okay, and we're gonna delete this XX, and we use this as its value. So all you do is each time you update, right? You update this value. So I have J1 and J2, right? And for J1 I have 3 values. For J2 I have at most 3 values. So I need to get them out. So next J1s, right? For n J1 in J1 minus 1, J1, and J1 plus 1. Okay, if nj1 is, so the requirement is 0 smaller or equal to this, and smaller or equal to n. Okay, then we have for nj2 in hold a second, maybe what I can do is Python has this. For nj2 in hold a second. Maybe I can do it better. In range, the start shall be maximum 0 and J1 minus 1, right? Awesome. And the end shall be the minimum of n and J1 plus 1, right? The minimum of the two, right? So we don't have to do this, we don't have to do this. Now we're gonna do nj2 in range, the same thing, but here I don't do the same. I shall say has to be out to the right of J1, right? It has to be to the right of J1, which means what I want is the maximum of J1 plus 1 and J2 minus 1, right? All the way to minimum n and then J2 plus 1, right? So the smallest will be J1 plus 1 if J2 minus 1 is to the left of J1, right? Otherwise, it will be that. So when we have that, then we simply say, do we even do? Nah, this is going to be, what the hell did I do? Man, these kind of mistakes are ridiculous. This is dp, okay? That is dp, and then the q is simply 0 n minus 1. Thank you. Right? That's right? Is that right? So we go through this. Right? We go through the queue, then we have a new temp, and then we have this. And basically we say, do we put this into temp? Right? Do we put this inside the temp? I do not know if we need to put in the temp. Therefore, the temp, these has to be a set. So we do have to have both. We need something to record current size, and we also need something to know which one we need to do the next time, right? So for J1, J2 in the queue, right, what we're gonna do is we will find its value, which is a dp, J1, J2, and we find it, and we need to add the current N1, NJ1, and J2. Then we get the new value for the NJ1 and J2, right? When we get it, I can say dp is equal to, okay, so I can use a default dict from collections, import default, default. From collections, import default dict. Can say dp equal default dict of an int. We can do counter, but it's fine. dp 0 and minus 1 is equal to, we do this, we delete this, and then we paste it here, and then delete this, right? And now we say dp, right, nj1, nj2 shall equal to maximum dp nj1, nj2, or dp n j1, j2 plus grid I j1 plus grid I j2, right? So we do that. Right, we do that. Then once we finish, right, then we say temp.add nj1, nj2. And then blah, blah, blah. Once we finish, we say q equals temp. Now we go through everything, right? We go through everything. We go through the last one. We go through the last one. Ooh, so We handle, and the last one is I is n minus 1. Okay, so we handle the j's. Once we handle, we're done. Now what we need to do is return the maximum of dp.values. Okay, so int is not iterable. How is it int? It's a set. It is int. It should be a set of this, right? Okay, let's take a look. Is this one correct? Not really. Not really. That's fine. Let me do some print debugging. Just get one of them. Answer should be 24. Okay, it's okay. This shall be grid. This shall be what? Cherry pickup grid. All right, what you want to see? What I want to see is well, what I want to see is the queue. So we'll print queue at the beginning, and we also want to see. I also want to see nj1, nj2. What did I do? And the dp nj1, nj2. Okay. All right, let's go. Python 3. Oh, I haven't quit this yet. Screw this. It's gonna be 2024. 02 challenge. That's good. Okay. So we start from 02. I can actually pull this up. Actually, I cannot pull this up because I didn't do it, but I can check here. All right. So we have that. Then 0, 1, 7. And then we have 0, 1, 0, 2. Now 0, 1, I get 13. 0, 2, I get 13 as well. 0, 1, 0, 1, 0, 2. And 0, 1, 0, 2. What about 1, 2? Why is there no 1, 2? Interesting. Why did I not have 1, 2? Interesting. Why do I not have 1, 2? Like this one never gets 1. Oh, gotcha. +1. Yeah, same thing. +1. Oh my god. Then we have a 1, 1. Okay, we need to avoid that. How do I avoid that? This I can take. Oh, I cannot take. I see. Here I can take this, right? This is fine. And here I cannot take this. I have to start from here. Right here I shall take all the way to j1 plus 1, right? And here I cannot take j1 plus 1. But actually, no. It depends. If this depends on what this nj1 is. Yeah, this is not right. It's nj1 plus 1, right? As long as I'm larger than nj1, we are good, right? We just need to be larger than nj1. And here is still okay. So let's try this. It's still not right, and I got a 55. Okay, 0, 1, 2. 1 2 1 2 1 2. Okay, so something is not right. Something is not right because I am doing here is not right. This is shall be nj1 nj2, right? nj1 nj2. Okay, let's try again. No, what the hell? DP is this one is we adding j1 j2 to nj1 nj2. That is correct, right? That is correct. And should be the maximum of current and whatever it is plus nj1 nj2. All right, let's just check. 0 2 0 1 0 1 equal 11. What the hell? What the actual hell? You're here, you're talking about 11. That's 4. Oh, it is 11. Right, it is 11 because this is 4 and this is, yeah, that's 11 or 7 or 13, right? Or 13. And next we can do 0 1. Next is this one, right? If we do 0 1, okay, I need oh, I see. Problem is we need to reset the DP. We need 2 DPs as well. Holy crap. All right, so temp Q. Okay, I need 2 things. So I need a temp Q. Okay. And I need a temp DP. And this is going to be temp DP, right? This is going to be temp DP equal to this. And temp Q add to this. And at the end, we'll do this. And DP equal to temp DP. And this shall be temp. Okay. Try this. Now we're almost there. Now we're almost there. We got 23 and we don't get 24. J1, J2, okay. Can do this, right? Do this. DP. J1, J2. Okay, let's try this. All right, so we have 0 2 go to 0 1, and this is 4 to 11, and then we have 0 2 to 0 2. That's 7. Okay, I agree. This is fine. Next level will be 0 1, right? So that's 11 to 6 and 17, or 11 to that's 21. Okay, 21. I have a 21. I don't see 21 anymore. Right? It should be a 21. To 1 2. And 1 2 become a 17. What is that? Stupidity. Oh, I know what that stupidity is. This is temp. So many error. There we go. Alright, so let's GCC this. And we don't need this. Okay. Alright, try this one. It's only, and it's correct. Yeah, pretty sure that is the solution. Okay, so what you had to say, my thing is, say, LeetCode 1463 DP, in which DP J1 J2 is the max value for any path ending at a certain row with J1 and J2 being the cell. Right, being the cells. We can use we use BFS, right? Use BFS to go through each row and a separate DP dict to record the max value for each possible J1, J2 pair, right? Each possible J1, J2 pair. Then the answer is the max value for all the J1, J2 pairs of the last row. So we have 4 loops, okay? 4. Now m, this one will run m times. Now this will run n squared times because it's all possible combinations, right? So this will, but these two, this will run at most 3 times. So we can just say times 9 at most. Okay. I think we can submit it. Pretty sure I solved this last time by myself as well. It's really not that complicated. So we can check this and check this and check this. So this is the first time I do it. Absolutely bonkers. A lot of but I think it's this, it's have just a lot of this, I don't know, search max. Don't have to do that. Bottom up. Yep, I think that is kind of the solution. Oh, bottom up, from last row and up. Current values. Yeah, it's alright. I like how I do it. It's yeah, reduce memory footprint. I mean, I use this, right? I use this. Do I have any advantage? Not really. Not really. Yeah, I don't think so. This is kind of, no, I don't like it. This is for robot 1, for robot 2. Huh, 3 levels. You know what? I think I like mine this time the best. It's based on a BFS kind of way to go through everything, and it just feels very neat, right? Easy to reason with. It's very few code, and it's easy to reason with. And we have the BFS part, we have the DP part. We set up a new DP every time, and then we go through this. This is just standard, right? We go, and this is we use the BFS kind of idea to handle it. All right, that's good. That's good. I'm pretty sure this is a standard solution because my previous solution looks very similar to this. It took a little while, maybe a little longer than I would like, but yeah, overall it's not that bad. It's not that bad. Yeah. Do 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 do. Yeah, it's the same runtime, so we don't have to sweat about it. All right, let's take a look at this one. Well, we already have 51 minutes, so I think I'll read through this. Could be a very good thing to think about before going to bed. Given two positive integers, low and high, represented as strings, find the count of stepping numbers in the inclusive range from low to high. A stepping number is an integer such that all of its adjacent digits have an absolute difference of exactly 1. Return an integer denoting the count of stepping numbers in the inclusive range from low to high. The answer may be high, so we have 2 modulo it. A stepping number should not have a leading 0. Holy crap. Oh my god. 10 to the 100. It doesn't really matter. Does not really matter. So the stepping numbers, each adjacent is at most 1. Okay, that's fine. And want to find how many are there. All right, let's draw it. Let's draw this. So we have 1 and 11. Yeah, that's not a good example, right? 1, 2, 3, 4, all the way to 10. That's... Oh, hold on. Inclusive. Oh, inclusive, so 1. Right, 1 to 10. Yeah, that's not like this 90 and 101. So we start from 90. 90 is no good, right? So we have to start with 9. So we don't have 98. It's possible. 2 digits, right? Now 3 digits, we start from 1. And the second one has to be, can be 2, or it can be 1. It cannot be 1, it can be 0. And a 1, 2 something already larger than this, so there's no go. So we do this. 0, and the next one can only be 1, so we can only have 101. So I have 2, 98 and 101. Basically, we have a low value, okay? A low value will be, something. Let's call it some D1, D2, D3, a 3-digit, okay? A 3-digit. And then we definitely start from D1, and you can always go 2 sides, right? D1 plus 1, D1 minus 1. And it check, right? If both satisfies, then we'll keep, right? If basically this is the second position, right? If both satisfies, or one of them satisfies, or and then we can keep bifurcate, right? We keep bifurcate. So eventually that's 3. So at most it's 100. Ugh. 100. You go 100 levels? Probably not. At a certain point, you will not be. But anyway, we start from certain, and then we do a certain amount. Then we get, right? Then we get, at least starting from this, how many do we have, right? So we get a total count of starting from this. And then we can say start from D1 plus 1, right? D1 plus 1, starting from this. So now what we need is an algorithm that can tell me, given a start, so it will be get count, right? So I can see a get count function will have the starting digit and number of digits, okay? Starting digit and number of digits will give me a count of how many stepping is within that. So if you give me 5, right? If I say a get count 5 and 3, you are telling me the total count from 500 all the way to 599. How many steppings are there? And we can use this, right? We can use this, no problem. And in fact, I think we shall do a get count, a start and end, right? But the both has to be the same number of digits. Then I can use this. So basically, if you give me a start and give me an end, and then I'll do whatever the start is, right? And then, like in this case, I'll just call get count 90 to 99 plus get count I don't know, 100 to 101, right? That's for here. So if you give me a low and give me a high, what I would do is I do the low, and then I'll do what? Like 10 to like it'll be like 1000 to 1000 to 1999, right? 2000 to 2999. So you have to go through all of them. So 1000, 2000, 3000. But I have 100. It can go to 100. I need something better. I don't. But does it take a long time to do though? I don't know. I don't think it takes a long time to do. I mean, okay, let's just see. If I have 1, let's say 1000, okay. I mean, if you start from 1000, you will definitely end as 1999. So it doesn't matter. You can just say start from 1000, right? So the second position, so we start with 1, and you can only have 2, and then you can have 3, and you can have 1, right? You can have 4, 2. Now you can have 0. Oof. 2, 0. Right? That's it. So we have 1, 2, 3, 4. 1, 2, 3, 2, right? 1. That's it. And a 1. 1, 2, 3, 1, 2. No, hold on. 1, 2, 3, 4. My bad. 1, 2, 3, 4. 1, 2, 3, 2. 1, 2, 1, 2, and a 1, 2, 1, 0. Right? That's 4. Is it always 4? Well, not necessarily, because if we start from 2, right? So 2, I can go 1 and 3, and 3 can go to 4, and maybe we can just write it out. 2, 3, 2, 3, 4, 5, 2, 3, 4, 4, and 4, 3, right? 2, that's it. That's all the 4s. And then we can also get 2, 1, 2, 3, 2, 3, right? That will be 8, right? 2, 3. That's, okay, 3 can go to 4, 3 can go to 2, and then we're done with 3. So now we do 2, 2. 2, we can go to, so 1, or I can go to 3, I can go to 1. 3, I can go to 2 things. So I can go to 2, I can go to 4. All right, now 1 can only go to 0. I can go to 0, and I can go to 1. I could go to 2. And then I can, that's all the 2s, right? That's all the 3s, all the 2s. Then I can have, no, I cannot have more. So that's 1, 2, 3, 4, 5, 6, 7, 8, 8, because each one I have 2 options, right? So this I have 2 times 2 times 2. So that's 8, right? That's 8. So starting from 2, I have 8 possibilities. Oh, but if I have like another digit, then some of them cannot move. Oh, that is the difficult part. So the difficult part is some of them can continue, some of them cannot. Interesting. Wait, what the hell is this 2, 2 thing? That doesn't make any sense. No, this is not right. You're not supposed to do 2, 2. Dude. Oh, I see some stuff. 2, 1. Right? Isn't that just a 1 with 3 digit? That's 1 with 3 digit. Right? So if I have a DP, which is the start, okay, and the digit, number of digits. If I call 1 DP1 3, that shall be just starting from a 1 with 3 digits, how many? And then I start with 2, I can know. I know, right? I know exactly. That seems more promising. That does seem more promising. And then all we need is a DP array. I mean, we shall start with 0 because it's possible. Because if it's 1, I can't have 0. I can have start with 0. I just cannot have a start with 0 from the start, right? Yeah, I think that is the thing, right? We try to find this. So when I have a low, I pick whatever it is, right? It's whatever it is, and then it cannot go low, so it can only go high, right? So in this case, I start with 90. I know the first is 9. So the next one I just need to call DP81. How many is that? So start with 8 with a 1 digit. The answer is 1. So with this I get 1, right? Now we're done with start with 9. Now we just need to bump up, right? Bump up. So now we can go to 100, 3 digits, right? 3 digits. So it's 2 digits, and we keep going by go to, the start. This one just plus 1, right? Plus 1 become 10, right? Become 10. So whenever it's 10, you just start with 1, right? We start with 1 and with 3 digits, right? Start with 1 with 3 digits. But in this case, because the high is this, right? The high is this, I need to stop and then be more careful when it's high. So the low we handle it, right? The low we handle it, and then the high we handle separately, and everything in between we just do it, right? So in this will be just DP, like DP23, right? DP23. DP23 will be equal to DP 24, my bad. 2 with 4 digits will be 3 with 3 digits plus DP 1 with 3 digits. Done. That's it. That's what this one will be, right? That's what this one. So we just keep doing this, and then we shall have a solution. Great. Great. We'll do this tomorrow or some other time. All right, that'll be it. I will end it today.